Now, in this slide, you are looking at a really large-scale steam power plant. And by looking at the size of small cars, and now you can appreciate how big this power plant is. And usually this kind of power plant is located in nearby a water source, and like a lake, as you see here, okay, because we need a lot of waters. And also you see this big tower that is water cooling tower, okay, and the water is circulated, from this water cooling tower to the condenser, which is located somewhere in this building to condense the water that is being used for power generation. As we discussed earlier, now water is really, advantageous in using as a working fluid for steam power plant because it's plentiful and cost is really cheap to use, non-toxic, and it's very chemically stable, and also that is relatively non-corrosive. And there are other kind of advantages in using water as a working fluid. However, we also have certain drawback to use it for the power plant. Particularly, we need to look at this. As we discussed earlier, in order to improve the network, the one way we can do is to increase the pressure, that is pressurized in the pump. Okay, and by increasing the pressure, we could increase the area surrounded by the processes. But if you really imagine that we just keep increasing the pressure, but at a certain point, the curve that takes the constant pressure in terms of the phase change from water to steam may go over the critical point, that is at the summit of the saturation zone. And this kind of process is called as the supercritical condition. And once your phase change process, becomes supercritical, it is not possible to discern the liquid phase and the vapor phase. So now let's take a look at these two images. So top image shows us the subcritical condition where we can see clearly the vapor separated from the liquid. But once we go over the critical point to make a supercritical, now everything is well mixed. So it's not possible to say that that is a liquid or vapor. It's kind of mixture, and that is quite hard to, still that is kind of the matter of, research. In fact, if we really make that your phase change process in terms of supercritical kind of process, it does increase the area surrounded by the processes. So we can get certain benefits by using the supercritical condition. But at the same time, if we want to use supercritical condition, it means usually that it is in very high pressure. So we need a special pipelines that can endure the high pressure and also high temperature. So even though that is really hot and very attractive in terms of research project, and we also working a lot about this kind of topic, but at the same time, still that is too early to use it for a really large scale steam power plant. So we somehow try to make use of conventional Rankine cycle that operates underneath the critical point, in a subcritical point, to generate a power at this moment. Now, with that being said, if you really look at the critical point of water, the critical temperature of water is around 374 degrees Celsius, and its critical pressure is around 22 megapascal. Still, that is really high, but if you really think about other possible materials, that is quite relatively low. So there must be a limit if you really want to use subcritical phase change in terms of the pressure that we can increase for water, and also there must be a certain limit in terms of temperature as well. Then how can you get over this limit? Okay, we want to still use the water as a working fluid because of a lot of advantages, but this kind of limit in terms of net power that we can gain is limited by the critical point as far as we want to use the subcritical phase change as our scheme. Then here comes a new idea. we have learned about the gas power cycle. And if you really recall what happens after expansion process and during the exhaust process, we kind of noticed that the exhaust gas temperature is still very high, and that really usually leads to a lot of waste of our energy. Okay, sometimes the gas temperature of the exhaust gas is it's very high, such that even we can generate steam by using this hot exhaust gas. So that is the main motivation of making up a combined cycle. So now, instead of using just one single cycle, what about combining two cycles? The one cycle operates usually at high temperatures, while another cycle operates in a relatively low temperature. Okay, so that is the main idea. So now let's try to combine, for example, a gas turbine and a steam turbine. Okay, one notice that I want to make here is that you don't really have to limit ourselves to using the only gas turbine. In fact, in island area or other isolated area or certain area that that are not that rich to operate a gas turbine, they many times use a diesel engine, not a small car diesel engine, but quite big diesel engine for gas for power generation. So as far as we have a gas power cycle that emits a hot exhaust gas, then this hot exhaust gas can be somehow used to generate a steam. So that is the main idea. Now, as an example, however, here, let's assume that we use a gas turbine and we use a steam turbine. Now, we have a gas turbine on top, and air comes in, compressed, and combusted and expands. Then now this hot exhaust gas goes up, and then usually it should be dumped away to the environment. However, now let's try to make use of this hot exhaust gas. But at the same time, let's think about the steam power plant. So now we need a pump, right? But instead of having a separate boiler, we can use the exhaust gas as a source to generate a steam. Now, what if we, lead these pipelines to the middle of the chimney, where the hot exhaust gas can go through those pipelines to transfer heat to a steam. And if this hot exhaust gas has sufficient energy, then this heat can boil the water and make a steam inside the pipeline. Then the steam flows to the steam turbine to generate power. And then the steam goes to the condenser and condensed and goes back to pump. So that is how we can combine the gas turbine and the steam power plant. So here, the key component that combines the gas turbine and the steam power plant is the heat exchanger that connects the chimney where exhaust gas flows and the pipelines where the water comes in and changes its phase to steam and flows to the steam turbine. And that exchanger is called as a heat recovery steam generator, or in short, HRSG. Okay? So in the HRSG, now steam can be generated to produce a power in a steam power plant side. Now let's take a look at this photo that I found in Google. We have three actually 1, 2, 3, and 4 units in the gas plant, the power plant, and those things are the air inlet to collect airs to flow that into the gas turbine. And in this middle area, then we should have a gas turbine. Okay, and as you see, and between the gas turbine and the chimney, we have like a big, gigantic kind of object, and that is a HRSG. So that is a bunch of pipelines, connected with a kind of, passage where exhaust gas flows. And from this HRSG, we can generate steam, and this steam can go to the steam power plant to generate more power. And another thing that we see in this photo is a condenser, as you see on the right bottom corner. Okay? So let's take a look at the HRSG more. And as I said, even though that looks quite simple in the schematic diagram, what it looks in reality is quite complicated because we have a lot of kind of pipelines, and we also have drums to collect the water and then take out steam and force. Okay? And the main section is kind of exhaust gas passage section. And in case when the exhaust gas temperature is not high enough, then there should be an auxiliary burner to make the temperature higher a little bit to make a sufficient amount of steam at high quality. Okay? Then this gas goes to the chimney to be emitted to the environment. Now, I hope that you understand how we can combine the gas turbine or in general gas power cycle with a steam power plant, okay, or Rankine cycle. Then let's try to take a look at the right-hand side, the TS diagram, to understand better about how we can combine in terms of the cycle analysis. Okay. Again, I'm going to use these indexes 1, 2, 3, and 4 for a Rankine cycle, and 5, 6, 7, 8 for the gas turbine or the Brayton cycle. So let's talk about the 5, 6, 7, and 8. And as you see, we start from almost the air temperature at around the room temperature. So from 5 to 6, we have compression process, and 6 to 7, we have heat addition to the Brayton cycle in the gas turbine. And now 7 to 8, we have isentropic expansion process in a gas turbine. And now, if we only use a single gas turbine as its power generation system, this 8 then is done. Your gas does not work anymore, and that is emitted as a exhaust gas to the atmosphere. And still, as you see, this temperature is quite high, a lot higher than even the temperature at 6, right? But instead of just emitting this hot exhaust gas to the surrounding, now we connect this gas with your water at the HRSG. So now let's take a look at, how can we draw the TS diagram for the Rankine cycle in a steam power plant. We have water, okay, at 1, and its pressure increases by going through the pump. Okay? Then we need to change that point, which is in the water, to the superheated steam. Okay, then how can you do it? Because by transferring the heat from gas to the steam at HRSG. So while this gas temperature goes down from 8 to 9, which is at the exit of HRSG, your water can increase its temperature, okay, and change its phase and even becomes superheated steam. Okay. Now you have to remember that 8 meets with 3 because it's counter flow heat exchanger. And now when the exhaust gas leaves the HRSG at 9, actually this is matching with the inlet temperature of water at 2. So because temperature at 9 is higher than temperature 2, yes, that still can transfer heat from the gas to the water. And now a temperature at 8 is higher than temperature 3. So still gas transfers heat to the superheated steam. Okay. Now the steam goes to the turbine to expand, and there is another vertical line of steam turbine. And we have condensing to reject certain amount of heat. So we have, if by combining these two cycles, we have one heat addition from 6 to 7, okay? And now we have net amount of work generated by the gas turbine, and another bottom cycle net work generated by a steam cycle, and we reject heat.
Now I move to the lecture note, where I show you the TS diagram again. So we have now the Brayton cycle and the Rankine cycle together in the TS diagram. And basically what you have to remember is that all the analysis of the thermodynamic cycles for both Brayton cycle and Rankine cycle in this case still remain the same. But what is the unique feature of the combined cycle is at the heat recovery steam generator, or HRSG. And what happens at the HRSG is, in terms of exhaust gas of the gas turbine side, is here, right? So at the HRSG, the exhaust gas temperature decreases from 8 to 9, and the heat loss due to this decrease of the temperature is transferred to the water side to increase its temperature of the water from 2 to all the way up to 3. So that is what happens at the HRSG. So now how can we get the thermodynamic analysis of the HRSG? And what you have to remember is, even though we have a different name called HRSG, its general concept is exactly same as heat exchanger. And we already learned about how to do the thermodynamic analysis for heat exchanger in the previous lecture note. So please go back to the lecture note and study how we do the first law of thermodynamics analysis for the heat exchanger and come back. Then you can actually understand better about what's going on at the HRSG. The core part of the HRSG is again heat from the exhaust gas transferred to the water. Now, by assuming assuming there should be no work component and potential energy and kinetic energy, both gas and water are ignored, and the first law of thermodynamics can be shrinked and simplified to the equation that we are looking at here. And the left-hand side is the amount of heat that is being lost by the exhaust gas. And this heat should be exactly same as the heat gain by the water. And the heat loss can be, or heat rejection from the gas side can be calculated by mass flow rate of the gas times enthalpy change from 0.8 to 9. And the heat gained by the water can be calculated by the mass flow rate of steam times the enthalpy from 2 to 3. So that is the amount of heat addition to the steam side. Then by dividing the entire equation with m dot g, we can convert that equation to the equation that we see in the next line. So H8 minus H9 is equal to F, that is a fraction or ratio, times H3 minus H2, where F, the ratio, is defined as the steam mass flow rate that is generated by the unit mass of gas, which is m dot g. Okay? So F tells us how much steam can be generated per unit mass of gas that is in the gas turbine side. Then how can you calculate the net work of the combined cycle? So there are two components that we have to think about the net work. One is from the gas turbine side and the other one is the steam turbine side. So when we use 1 kilogram of gas in the gas turbine side, then the total amount of net work is the net amount of work for the gas turbine side, and per unit mass of gas, we generate F kilogram per second of steam. So we have to multiply F times the net work per unit mass of steam, that is W net, steam. So let me write it down. So that is net work per unit mass of steam, right? So by multiplying F to that value, then we can calculate how much net work can be generated by unit mass of gas. And in order to calculate the net work for the gas turbine, we have to calculate the turbine work, which is gas turbine work, minus compress work. And for the net work from the steam turbine is steam turbine work minus pump work. Also, we can calculate the thermal efficiency, okay, which is defined as net work divided by Q in. And Q in can be calculated by H7 minus H6. That is the amount of heat addition in the gas turbine. And we just fully use that to even generate a power in the steam turbine as well.